Okay. Okay, so you've seen this symbol before. Sure the mic's still working. Yep. Okay, you've seen this symbol before. That means infinitesimal change in y divided by infinitesimal change in x. It goes back to the idea of the Desmos demonstration, that when the dots are, the two secant slopes are separate and distinct, we're actually calculating, let's draw it over here, when we're looking at Desmos like that, we're actually calculating for this like blue slope here, we're calculating the change in y divided by the change in x. And as we move, we make the points get closer and closer. What happens is we are making delta x get closer and closer to 0 because the 2 points are getting closer and closer together. When those 2 points become what is known as infinitesimally close, dx is no longer dx. Delta x is no longer delta x. Delta x changes to dx. So these two things have basically the same meaning. They are a difference in x values, but this difference is finite and distinct. This difference is infinitesimal. Once we know that difference, we can calculate how far apart the y values are. That's what dy is. And this is tangent slope. This is derivative. Please, come in.
So would the value of d of x always have an approximate value of 0?
The better way to think of it is dx has a value that is, as best I can describe, 0.000 forever 1. So dx, 2 for Cameron. Dx is never 0, but it is the limit as x approaches 0, as dx approaches 0. Perfect. Okay, please. Yes. So let's use this little device here. See if it'll work. Sometimes it works, sometimes it does not. Anybody else? Okay. So that's what that means. It just means the tangent slope of f. This symbol here, I've not shown you yet. This just means the tangent slope of f prime. So this is equivalent to saying f prime roughly. This is equivalent to saying f double prime roughly. So you're looking on the graph above to identify if this is the graph of f, this is saying where would the tangent slopes of f always be positive? On what interval? Raise your hand if you know that. So look up this graph of f, or look at your blue sheet. This is simply saying where on that graph of f is the tangent slope or rate of change going to be positive? Hands up. You're looking for intervals, like from what interval, from what point to what point will the tangent slope of this f be positive? Hands up. Most of you, still not everybody though. Just keep your hand up for a minute. If you're not seeing it, here's different ways to do it. You could do this. You could say, okay, right here the slope of f is positive. So that would count. That would match up with this. And then you just keep going. You say, oh wait, right here the slope of f is also positive. That still matches. Keep going. Right here the slope of f is still positive. That still matches. That's one way to solve the problem. Hands up. Who knows on what interval is this going to be true? Where is the slope of this f going to always be positive? Hands again. Show me hands. I got a few more that didn't have their hand up before. Let's go, Eliza. Yeah.
A.
So at A for sure. And then you just keep going. And tell me where does f stop having slopes that are positive, Eliza?
Like at the top of C.
Perfect.
Where it's 0.
So from here to here, f has a slope that is always positive. You can see it on the graph. 2 points if you knew that. So from here to here, f has a slope that is positive, from A to C. Questions? You could have also used Danica's chart. You could have said, oh, wait a minute. When the graph of f has increasing y values, which is all like this, that's where the values of f prime will all be positive. And you get the same result. Danica's chart is just a quick way to summarize what we've been talking about. So, questions? Please.
Wait, so on Danica's chart, you see the top three equations.
Uh-huh.
Is that third one equal to that notation in the question?
Essentially.
Essentially, because like I know x and t is probably referring to like y basically.
Correct. Good. Two more, please. Ashton.
My question is, you can kind of see like from B to C, it's still like increasing y values, but the slope is actually getting less positive.
Let me draw it out. That's accurate. From B to C, f is still increasing. The y values are going up. But from B to C, the slopes of f are decreasing. Because this slope here is positive, but then as you move along, you can see the slope becomes less positive, and then the slope becomes even less positive. So in this region, f is increasing, but meaning the slopes of f must be positive, but the slopes of f are decreasing. That's because the curvature of f has switched to concave down. That's perfect. Two more, Cameron.
And point B is an inflection point, yes.
Correct. Two for Cameron. Look, everybody, what you're starting to do is exactly what you want to do in this class. Like those kinds of questions are like perfect. Like you're just looking for, because again, I keep reminding you, I'm not training you to solve a problem. You'll learn very quickly that you see old AP problems, they're very unique. Like they use it one year, they never use it again. And so you've got to get used to seeing something new, but applying it. So doing what Cameron's doing is really, really smart. He's like just continually just analyzing what's going on. Hey, wait a minute. We learned about inflection points. X equal B is an inflection point of f because it is where the concavity of f is changing. It's perfect. There you go. Okay, so we've answered this. We know that, let's see, the slope of f, that's what dy dx means. The slope of f is definitely positive from A to C. The slope of f is positive from A to C. F is increasing from A to C, therefore the slope of f will be positive from A to C. Now you need to figure out where is the second derivative of f negative. There are different ways to do this, but here's the fastest way. Danica's chart. Danica's chart says that the second derivative of f will be negative whenever f is concave down. So really, they're just asking me to identify on what intervals is f going to be concave down. That's all they're asking for. Hands up. Who knows when f is concave down? What's the interval where f is concave down? Hands. What's the interval where f is concave down? Most everybody again. Let's go over here to Gavin.
After C.
So C and onward, two for Gavin. F is definitely concave down, but small error. That's not only where f is concave down. Hands up. What's the full interval where f is concave down? There we go. Let's go, Susanna.
B to D.
So from B to, say letter, Susanna.
B to D.
Thank you. From B to D, do you see it, Gavin? How many knew that one? Two more, okay. B to D, that's where f is concave down. So B to D, from B to D, f is concave down. Questions? Yeah, please.
I can understand why like d of y and d of x, like how that represents a tangent line, but mathematically, like how does d to the second y over d to x? Like I'm trying to figure it out, and the d's are canceling out, and I'm just confused.
Good call. Hey, look up, everybody. 2 more from Michael. Look. So, a couple of things you can't ever do. You can never use this foul word, so don't do that. It's okay, you're getting used to it. You can't do this. This is not d multiplied by y. This is not d multiplied by dx. Dx means the infinitesimal change in x values. Dy means the corresponding infinitesimal change in the y values. So the d's never divide out. Yeah, you can never do that. Whether you call it canceling or dividing, whatever, doesn't matter. They just don't divide. Because it's not d divided by d, it's dy divided by dx.
So the d is representing just like, it's more representing the limit, it's not representing an actual number.
Yeah, the d goes with the, that's the wrong button. The d goes with the y. We gotta fix something there. I hit the wrong button. Just a new page, that wouldn't be so bad. Thank you. I'm trying to keep track of too many things at once. So the d's never divide. Is everybody good with that? The d's never divide. This is confusing because it does not mean d squared. I looked for like 45 minutes trying to find an answer to like where the heck this thing came from. I've never found a satisfactory answer. So I kind of did my own analysis, and this is what I came up with. So this might be accurate, but it also might not be. It's just my analysis. You've got dy dx, right? What that really means is you're going to find how much the x value is changing. And once you know that, you're going to find how much the y value is changing. So another way to write it is like that. Now, they're not multiplying, but they will say that that can be written more concisely like that. So that's kind of where dy dx comes from. You're going to go find the infinitesimal change in x. You're then going to calculate how much that change in y is and compare them. So
in this situation, why have the d then? Because an infinitesimal change in x would also have an infinitesimal change in y.
it's just whoever invented the symbols, they decided to do that. So you could do this. You could say, rather than find this compared to that, let's go do this same operation to what we just did, dy dx. Let's do it again. Let's find the slope of the slopes. Well, that kind of looks like d is being squared. But it isn't. It just kind of looks like it. This kind of looks like dx is being squared. So it kind of looks like we should have written it like this. But it's not being squared anyway. So I think they just said, we'll just go like this. I don't really know where it comes from, but that is kind of an explanation. Please, Kim.
So the exponent is telling us which f of prime we're finding?
Nice. 2 more for Kayla. That's all this is really telling you, Kayla. Because they could do 3, 4, 5, whatever. That's perfect. Anybody else? Hey, so finishing off this problem, is that kind of okay for now, Michael?
Yeah.
Okay. We know that, the slopes of f are positive when f is increasing. That's from A to C. We know that the second derivative of f will be negative whenever f is concave down. Now that occurs here from B to D. Therefore, both items are true only from B to C. So the correct answer is right there. Oh, please, Cameron.
Can you graph f prime and f double prime?
So, I must confess that I'm not really good at graphing them because they don't require it on the AP test, so I don't practice, but I'll do my best. The slope of f, right here, is some positive value, and then the slope of f is then becoming more positive. And then again, more positive. And then the slope of f stops becoming more positive and starts to become less positive, and then 0. So I'd probably start with the fact that at x equals c, wherever that is, so at x equals c, the slope of f, so we got a, b, c. And then d. Okay, the slope of f at x equals c is 0. So if I were graphing f prime, I'd put a dot right there. I'd say prior to that, the slope of f was positive, more positive, and less positive. So it's got to like go, the slope of f is positive, it gets more positive, but and then the slope of f has to become less positive until it gets down to 0. I don't claim that to be good at all, because I'm not practiced at this. Then the slope of f is negative and becoming less negative forever. So it's going to go like that. That's kind of a picture of f prime. I wouldn't call it a really good picture. Anyway, Tom?
Wouldn't it have one less concave since it's the prime? So wouldn't it just be like a concave down the entire
Oh, maybe
way?
so. Like just like this, you're saying.
Yeah.
Just like that. That would work. It wouldn't have to have that little concavity thing too for Tom. We're running out of time. I have to think about this.
What problems are we supposed to be answering this one?
Good question. Look up. Everybody look up. So the homework assignment is not due. Don't leave.